it is my great pleasure to introduce our second plenary talk from Dr. Benny Mikkelsen. Benny could be called a serial entrepreneur. He is the founder and chief technology officer of Acacia Communications, a successful startup focusing on coherent optical interconnect solutions. Prior to joining Acacia, Benny co-founded Mintera and served as vice president of technology. And before that, he held various engineering roles at Bell Labs. Benny has published more than 200 papers. He holds a master and a PhD in electrical engineering from the Technical University of Denmark. Benny's talk focuses on photonic integration and digital signal processing. These are key technologies to support ever-increasing need for higher data rates and smaller, more cost-effective optical modules. Benny will provide an outlook on the challenges and opportunities the industry is facing and how co-packaging of optics and electronics. Please welcome Benny Mikkelsen.
Thank you very much for the kind introduction. And thank you very much to OFC for inviting me to give this presentation. It's a true honor. I believe this is my 32nd OFC in a row, so being here as a speaker is truly an honor. As the title of my presentation suggests, I'm going to discuss how electrophotonic integration can help tackle capacity and density challenges in optical network. In particular, we're going to discuss how photonic integration can help in transport, how it can help in short-reach applications, and even how it can help bring in bits in and out of switches in a cost-effective and power-efficient manner. But let's first discuss some of the key drivers behind the increase in capacity and density requirements. And as you probably all know, more users, more devices get connected every day, requiring higher and higher speeds, and also we consume more and more video content everywhere globally. And on the horizon, we have new services like self-driving cars, we have augmented reality, we have healthcare, and we have Internet of Things coming, increasing further demand for capacity as we go forward. And also, there are several reports showing that capacity roughly grows between 25% and 30% year-over-year. And also, there are several reports showing that network operators spend roughly 7% more on capital equipment, on networking year-over-year. On the optical transport segment, roughly 3% get spent more every year. And on optical transceivers themselves, roughly 10% increase year-over-year in sales. So the good news here is we get paid more and more every year. However, the challenge is traffic is growing even faster. So innovation has to bridge that gap between what we get paid for and what we have to deliver. And electrophotonic integration is certainly key to achieving that. Also important to notice that the total cost of ownership is not just the cost of the equipment, but also the cost of operating the equipment. And part of operating the equipment is the cost of space, the cost of cooling, and also the cost of supplying electricity and power. And there are some forecasts predicting that in 10 years, actually 20% of the global electricity is going to be consumed by information technology, in particular consumed by data centers and wide access network. So obviously, on a high level, there's a strong interest in decreasing power consumption of telecom equipment. Also, if you look at it more in a, so to speak, localized, inside a data center or central office, if the equipment is consuming too much power, you can have hot spots, meaning you can have half-empty equipment. And as we scale capacity, and if we don't take care of power consumption at the same time, we could end up in a quite unfortunate situation. So clearly, we need to also take care of power consumption as we scale capacity. And fortunately, integration, or history has shown that integration is a very, very powerful way of not just increasing capacity, but also at the same time reduce size, power, and cost. For example, 60 years ago, we had the world's first computer. It was quite limited in processing power, took up the space of an apartment, consumed an enormous amount of power, and was quite expensive. Whereas today, we can get an iPhone, do many more times of processing, very power efficient and actually affordable at the same time. So integration has shown to us we can increase capacity while at the same time we reduce size, power, and cost. So how does this apply to optical networking? Well, when we talk about optical networks, we really have two key components, right? We have electronics and we have photonics. Let's start by looking at the electronics first. So in the electronic domain, we have Moore's law, meaning we have a generic building block, meaning a transistor that shrinks on a pretty consistent time frame. Every time we go into a new CMOS node, we get a smaller transistor, meaning we can integrate more and more of these transistors onto an ASIC. As a matter of fact, today, we can integrate billions of transistors onto a single ASIC. And we believe this Moore's law will continue for quite some time. We are, however, changing transistors. In old days, we used planar transistors. Now we're going to FinFET, and going beyond 3 nanometers, we might see a new type of transistors. But we believe Moore's law will continue for quite some time. Going to the optics side, we cannot yet integrate billions of optics functions. We can integrate hundreds of functions, shown here by some pioneering work by Luxtera on silicon photonics and Infineon on indium phosphide. One of the challenges we have in the photonic domain is that we don't have a single building block, right? We need to both build lasers, modulators, receivers, and splitters, etc. So there are many, so to speak, different building blocks. And also we don't have a common material system like CMOS. And also we don't have this dimensional scaling working for, so to speak, the electronic guys. We are limited by the wavelength of light, so we cannot truly shrink things arbitrarily small. So the net of all this is we really don't have a Moore's law for optics. So what that really means is that optical engineers have actually to be more creative than the electronic colleagues. And as you'll see later on, they are actually doing a very great job, as you'll see later on. So how do we integrate electronic and photonic? Well, there are really two main concepts. You can do monolithic integration, where you integrate electronics and photonics in a single process, typically silicon. And there are some examples here to the right, showing some early work and pioneering examples. The other approach is to do heterogeneous or co-packaging, in which case we can either take the photonic and electronic, put them on a common substrate, we call that 2D, or we can put them on an interposer, and we call that 2.5D, or we can start stacking them, in which case we call it 3D integration. And again, here to the right, there are some early interesting examples of how we have done that. In the coming slides, we're going to show more details on or examples of how we integrate electronics and photonics. So how can optical networking benefit from electrophotonic integration? Or put differently, how can such a network as shown here, where we have front haul, back haul, metro, long haul, subsea, we have a data center part of the network where we have data center interconnect, campus, you might have a data center where we have racks of servers, and we have, assuming a leaf spine switch architect inside the data center. How can we, so to speak, optimize capacity of that network while at the same time reduce cost? Well, if Shannon could call Moore, I believe he would ask Moore, how do we get closer to my capacity limit? And I'm pretty confident that Moore would answer more and more integration. And in the remaining part of this presentation here, we're going to show and discuss how true that in fact is. And we're going to do that by putting a bit on a journey through this network. So we're going to have this bit travel through the network, and as it travels through the network, we're going to see how it benefits from electrophotonic integration. And we're first going to put it through the transport part of the network, which we define as distances from tens of kilometers to thousands of kilometers. We're then going to discuss short-reach applications, which we define as less than 10 kilometers, and typically is gray optics or non-dense WDM optics. And then finally, we're going to discuss how electrophotonic integration can help us getting bits in and out of switches in a power and cost-effective manner. So let's start this journey, and let's start first with the transport part of the network. Let's first discuss some high-level trends in transport. So clearly, transport is becoming coherent. All interfaces in transport today are coherent, and what we are benefiting from coherent is an increase in capacity. We have roughly increased capacity by a factor of 12 by introducing coherent, the factor of 2 coming from adding the extra polarization, and if we use, for example, 64 QAM, we get another factor of 6. So in total, a factor of 12 improvement in capacity. However, we are getting closer to Shannon, so it's becoming more and more difficult to increase capacity and reduce cost by a bit by just going up in constellation size. Once you go beyond 64 QAM, your distance really start to shrink dramatically. So we really left with, from here on, really moving up in baud rate to speak, increase capacity or reduce cost per bit. Another trend we're also seeing is disaggregation, is interoperability. It's putting dense WDM interfaces onto routers and switches, all of which require pluggability or requiring putting optics or coherent into small pluggable form factors. And in order to do that, we need to reduce power and size of the optics, which in turn, of course, drives integration. Coherent is really an ideal application of electrophotonic integration because there are so many optical functions, as you can see to the left. There are high-speed drivers and TAs, high-speed analog and digital converters. There are many high-speed analog interfaces, and there is a very big advanced digital signal processor sitting in that coherent receiver as well. So how can we integrate this coherent transceiver? And there are really two main approaches to that. One is an indium phosphide approach, and the other one is a silicon photonic approach. In indium phosphide, we try to integrate everything but the DSP. In the silicon photonic, we keep the laser aside and try to integrate everything else, including the DSP. And both approaches have pluses and minuses. The indium phosphide have native gain and can eliminate this fiber interconnect between the fiber and the remaining part. The silicon photonic can take advantage of being rather insensitive to temperature, and also since we now can integrate the DSP, we can eliminate high-speed RF interconnects between the DSP and the remaining parts. So each have pluses and minuses, but I believe both have achieved pretty amazing results. And a couple of examples are shown here. One from Finisar to the left, where they have been able to integrate everything inside that green box into a small form factor the size of a quarter. To the right, VLKs have been able to integrate everything but the laser, meaning the DSP and all the optics, onto a common substrate, into a non-hermetic package, also the size of a quarter. But it clearly looks like we all like to compare the size of our parts to a quarter, and I believe it should indicate the size, not the cost of the part. Yeah. So another way of looking at the benefit of electrophotonic integration is by seeing how have we been able to decrease the size of real coherent transceivers over time. What I'm showing here is a very early generation of a coherent transceiver back from 2011 and 12. And as you can see, there are many discrete components inside one of these transceivers. You have a lithium niobate modulator, you have external driver, you have a coherent receiver, you have a DSP, and you have an external MUX because we didn't have DACs at that point in time. And also we even have cables going through between some of these components. So a lot of individual parts. Later on, we have been able to integrate many of these functions into much smaller blocks. For example, we've been able to integrate all the optics, the modulator, the drivers, the receiver into a small gold box shown here to the right in that CFP. And also we have been able to integrate the DSP and the electric mux, which is now becoming a DAC, into one DSP or one ASIC. And at the same time, taking advantage of moving from 40 nanometer CMOS to 28 nanometer CMOS, so we could shrink the size of that DSP as well. We've taken this one step further, where we now have been able to now integrate the DSP and the optics into one common package. And we are now able to put that into a CFP2 and have it work now at 200 gigs, so doubling the speed, halving the size. And if you open up that, or take the lid off that small box, building blocks, you'll see that inside you have a single substrate. On that substrate you have the DSP, and it's sitting next to the optics, which is silicon photonic based coherent receiver, all the modulators and receivers, and you have TIAs and drivers being stacked on top of that silicon photonic die. So 3D stacking. And again, you can see this is about the size of a quarter. And this is really the entire coherent receiver. If you add now an optical power supply, meaning a laser, and an electrical power supply, then you have a complete coherent transceiver working at 200 gig today. And we believe in the near future, we'll be able to put this into an even smaller form factor, a QSFP or OSFP-like form factor, and we also at the same time will be able to double the speed. So putting 400 gig into the same kind of form factors as being used for client optics. And I'd like to point out, this is not just our company working on this, the entire industry is working today on putting 400 gig coherent into these small client form factors. So some of the key trends behind what I just showed. So what I'm showing here to the left is how power, size, and cost have evolved over these many generations. And as you can see, on the per 100 gig basis, and as you can see, we've been able to reduce all these parameters roughly by 30 to 40% year-over-year. Actually beating Moore's law. And if we predict forward, then in 3 or 4 years, the power consumption for per 100 gig for a coherent interface will be actually less than 1 watt. The interesting thing to look at would be how are the relative power consumption between the DSP ASIC and the optics in one of these transceivers. And this is shown to the right. So what you can see here is that actually the power consumption, or relative power consumption, is actually about 50-50%. And this has stayed constant over time. So even in the old days, it was 50%, and today is 50%. And when we move into this 400 gig in a QSFP form factor, it's still going to be 50%. And that's actually quite amazing that the optics has been able to keep up with the ASIC, despite there's no Moore's law for optics. So it actually shows optics engineers in this room are extremely smart. And what they have been doing is providing us with much more efficient optics. They have been co-optimizing drivers and modulators, getting rid of 50 ohm interfaces. They moved from gallium arsenide to silicon germanium type of drivers. And also, very important, and sometimes we forget it, is the control electronic in these ASIC or coherent interfaces takes up a lot of space and are quite costly as well. And what we have been doing is integrating all these discrete components now into a single controlled ASIC as well. So here are some of the key techniques we are using to reduce power, size, cost, and at the same time increase capacity. So Moore's law helps us everywhere, but on the power savings, eliminating interfaces, in particular eliminating 50 ohm interface is key. To reduce size, co-packaging is key, but also, as I discussed before, integrating all the control ICs are quite important. And showing an example here to the lower right, where showing one of our CFP2 form factors, where the red to the left is the discrete implementation we did in the old days, and now by integrating all these discrete ICs into one control ASIC, we have saved 500% in the space, and I believe an equal amount in cost. So cost reduction comes from eliminating separate gold boxes, meaning co-packaging, and also increasing the baud rate. As we double the baud rate, costs don't double at the same time, so we save on a per bit basis. To increase capacity, we need to have even more advanced digital signal processing and also go up in baud rate. So what are some of the future trends we're seeing in electrophotonic integration? Well, one is going to higher and higher baud rates, and here to the right we have plotted what is the FT for various CMOS processes, both in the past and going forward. And we can see that in 5 nanometer, we're going to have an FT that can actually support A2Ds and DACs that can support 130 gigabaud speeds. So in 5 nanometer, which is going to be available next year, we are actually able to, from an ASIC perspective, support 130 gigabaud. And as you can see from the lower figure, the optics guys are also keeping up, showing that you can actually do 130 gigabaud from the optics as well. So we believe that in a year or two, we're going to see this very high baud rate system coming to market. And of course, very high baud rates require extremely tight, so to speak, integration of both the ASIC and the optics. Another trend or requirement we're seeing is really low cost 100 gigabit coherent interfaces. 100 gig is going to stay around for a very long time, and the new service like on the edge, 5G as we just heard about, Remote PHY or cable are really driving the need for this very low power, small pluggable coherent interfaces, ideally in a QSFP form factor that consumes less than 4.5 watts. So clearly, electrophotonic integration is going to be key in achieving those targets. Now let's move on to the second part of our journey. Let's move inside the data center. Let's move on to the campus. Let's move in below the 10 kilometers. So here, hyperscalers today are clearly driving the new technology and the speeds. Carriers drove 100 gig, but hyperscalers are clearly driving 400 gig. Clearly, we're seeing a trend towards multi-level PAM4 with digital signal processing at 400 gig. And if you look at some of the, so to speak, key technology behind the electrophotonic integration we are benefiting from in the data center, it's shown here to the right some examples. One is integrating in the optics, in the phosphide, modulators, lasers, and the optical muxes. There's another example here from Luxtera, doing some pioneering work in silicon photonic, and also example of actually monolithic integration of drivers and modulators as well. However, I think the key trend inside data centers and short reach is moving towards multi-level, and truly also believing that coherent eventually will move to shorter and shorter reach as we move up in speed. Not just because coherent adds 4x in capacity, but also because it allows much more efficient equalization, so you can actually live with non-perfect optics as well. And if you look at the complexity, it's very similar to PAM4. The main difference is really between PAM4 and coherent. For PAM4, you need 4 lasers, non-coherent lasers, whereas for the coherent, you need 1 coherent laser. So if you can make this laser similar priced as 4 non-coherent lasers, coherent will be quite cost competitive. And we believe also it will be power competitive. We believe you can put 800 gig into a transceiver that consumes less than 18 watts with 5 nanometer CMOS. So as shown here in the lower right figure, as we move up in speed, we predict coherent moving to shorter and shorter distances, and maybe above 800 gig, it might even move inside the data center. All enabled by electrophotonic integration. Let's move to the final part of our journey inside the data center. Let's see how we can help moving bits in and out of switches in a very power and cost-effective way. So let's look at some trends on switches. Switches are getting bigger and bigger, and here to the right there's a roadmap from Broadcom showing that today they're shipping 12.8 terabit switches, soon shipping 25.6 terabit switches. And as these switches get bigger and bigger, to keep the pin count under control, you have to increase the lane speed into these switches. And that creates challenges. You have additional electrical losses when you have these connections running on your PCB, which in turn require more equalization, which in turn increase the power consumption. And the switching functions already consume the majority of the power in the network. So obviously there's a strong interest in how can we reduce the power of moving bits in and out of these switches. And here's an example from Facebook on how their, so to speak, cards look like inside the data center. Shown here, when you go from a switch, typically in their network, to the front panel, you have to go, in some cases, through a connector, and you need to have retimers and gearboxes, which also consume power. So it's actually quite power consuming to move a bit from the switch to the front panel, typically consuming as much as 6 picojoule per bit. Also, if you keep using 400 gig pluggables and put them on the front plate, then beyond 12 and 8 terabits, you now have to move up to 2 rack units. You cannot fit 25 terabit or 50 terabit in a 1 rack unit line card with 400 gig interfaces. You would run out of space on your front plate. So what are the options? Well, there are really 3 options. We can keep doing what we are doing today, meaning putting optics on the front plate and use pluggables. Or we can go to onboard optics, as shown here in the middle. Or we can do co-packaging of the optics and the electrical switch, meaning putting them on a common substrate. An example of that is shown here to the right. It's an example generated by Chris Dorr, showing that you have a 50 terabit switch on a common substrate with 16 chiplets, and each chiplet support up to 3.2 terabit of capacity by supporting 8 400 gig either FR4 or DR4 interfaces. Now, since we're putting these optical interfaces very close to the switch, we can now use a extreme short reach interface consuming significantly less power. Also, you can see these chiplets are sitting in sockets, so they're actually pluggables. Also, you can see actually we are relying on using, so to speak, a laser bank or remote lasers. So we are assuming the lasers are sitting in a, so to speak, a cooler area, and all the lasers are being shared between these various chiplets. Also, you can see from the lower right figure that we had to, so to speak, use very advanced integration technique, including 3D stacking and also requiring true silicon vias on the silicon photonics side to make this happen. So this truly will, so to speak, challenge our integration, so to speak, effort. Now, expanding the view of that chiplet, you can see one of these 3.2 terabit chiplets will contain 4 8-channel TIAs, 4 8-channel drivers sitting on top of the silicon photonic die, which have all the modulators and receivers. And in front of these, you have the 32 LEDs and DACs, including the PAM4 DSP processing needed. Also, since these chiplets are actually pluggable, you could consider some of them being coherent, right? So you could, for example, in some cases, transmit over hundreds of kilometers, and in some other cases, you use the short reach where you go maybe 2 kilometers. So what do we gain from co-packaging of the optics with the switch? Well, let's first take an example of where you, in the old way, where you put the optical pluggables at the front panel, as we're doing today. And let's take an example of a 50 terabit switch, in which case, if you use 400 gig pluggables, you'll need 128 of these pluggables, shown here. And if you calculate the power consumption of the ASIC and the optics and the interface, the total power consumption will be close to a little bit less than 2,000 watts. And it requires a 2 rack unit line card. Now, if you replace that with a co-packaging of the ASIC and the optics, then as shown here by an example from Luxtera, where they are, so to speak, predicting how it will look like if you were to integrate the optics and the switch, then you'll see it easily fit into one rack unit slot. And you also see that because we now get rid of these long interfaces, we also save power on these electronic interfaces. So the net result, the total power, is going to be now 20% smaller than what we saw before. So we save really 100% on the height, and we're going to save another 20% or 50% on power as well. And there's going to be additional power savings from shared lasers and also from shared processors, control of all the PICs in each of these chiplets. And there are also going to be significant cost savings from shared PCB, power regulators, the shared lasers, etc., etc. So those are the key reasons why the industry today is spending a lot of effort and time on making this come through. So let bring me on to the final slide of this presentation here, which is kind of a summary slide. So electrophotonic integration has already enabled cost-effective scaling of capacity and density in optical networks, and we believe we'll continue to benefit from smaller CMOS nodes well beyond the 7 nanometer we are in today. Monolithic integration and 3D stacking is in its early phases, but we are already seeing this bringing significant value to coherent interfaces today. It has enabled small pluggable form factors and will continue to enable even smaller form factors as we go forward. As an example, 400 gig in a small QSFP or OCP form factor very soon. Co-packaging of optics and switches is expected to be key for at least 50 terabit and beyond. And also, we didn't cover that today, but there are many other applications where electrophotonic integration can benefit or can help, including OCT, optical coherent tomography, LiDARs. I'm sure we're going to hear in the next talk that also that can benefit enormously from electrophotonic integration. And finally, also, there are some examples of where people are taking a number of silicon modulators, combining with electrical integration, and building basically a key element for deep learning or artificial intelligence. So many applications coming for electrophotonic integration. And that brings me on to the very last slide, which is thank you very much for your kind attention.